What's up, everybody? We're here in organic chemistry where we're going to be doing experiment 4C. Get ready.
In this lab, we isolated a neutral, basic, and acidic component from an ether solution through solvent extraction by turning it into its conjugate, the effect from the solution by the exception or donation of a proton so that we could isolate it. Solvent extraction is the technique of separating components into two immiscible solvents, in this case water, and our organic solvent ether. It is useful in the food industry as well as isolating natural products that are used in pharmaceuticals for medicine. We use benzoic acid as our acid, ethyl 4-aminobenzoate as our base, and 9-fluoronone as our neutral substance. The components were all solids, and due to not being able to dissolve in water, filtration could not pass the large particles through the filter paper. Our first separation was of the basic component ethyl 4-aminobenzoate. We wanted to be able to make ethyl 4-aminobenzoate water-soluble as it is currently ether-soluble. First, we added 50 milligrams of each substance to a 15 milliliter centrifuge tube. We're recording our video, no funniness.
We're going to add a mixture of 9-fluoronone. I'm going to edit this at 3 a.m.
Okay, so Then, in the hood, we added 4 milliliters of diethyl ether, the organic solvent that is immiscible in water, using a 10 milliliter graduated cylinder, and we mixed the solutions together with a vortex mixer. We cooled the solution in an ice bath. To separate the basic component, which is the ethyl 4-aminobenzoate, from the solution, we added 2 milliliters of 3 molar HCl. Ethyl 4-aminobenzoate now becomes ethyl 4-benzoic acid due to an accepting of the proton from the acid. We mixed with the vortex mixer and then vented. After the layers separated, we removed the bottom aqueous solution using a Pasteur pipette and transferred it to a labeled 10 milliliter Erlenmeyer flask. We repeated with an additional 2 milliliters of 3 molar acid solution to get any remaining basic component. As you can now see, and this is through solvent extraction, whenever you add an acid to a base, the base becomes its conjugate acid, which now makes it an ion, which is water soluble. And then the acid from HCl now becomes a conjugate base. We transfer the aqueous solution to the same Erlenmeyer flask, stopper the flask, and save the ether solution. The aqueous acidic solution will be used in the next step. It is also important to notice that in this lab, the organic layer was less dense than the aqueous layer, which contained the ethyl 4-aminobenzoate, which is why it was easy to extract from the bottom.
Virginia, progress report. What are your thoughts on the lab so far?
It's great.
Guys, make sure to wear goggles. Lab safety. Mr. Palmer.
Hey there.
Gonna be our lab report?
Yeah, I'd love to be.
All right. Say something cool. You took too long.
That was good, right?
Yeah, that was good. That was good. That was good.
To extract any more of the ethyl 4 that is still in there.
He's doing a trick. Uno, dos, and then he left without a trace.
Pretty good. In order to isolate the basic component ethyl 4-aminobenzoate, we added 6 molar NaOH, which is a conjugate base, to the conjugate acid of ethyl 4-benzoic acid, dropwise until the alkaline turned the litmus paper blue.
This is our goal. Right now we're here. We need to go here.
We were essentially trying to add a concentrated base to crystallize the original solution that was then weighed. As you can see from our separation of the basic component, we have ethyl 4-benzoic acid, but by adding its conjugate base of NaOH, the removal of a hydrogen from the conjugate acid turned it back into its ether-soluble ethyl 4-aminobenzoate, and the hydrogen bonded with the OH- to give water as a product, and also the Na+ bonded with the Cl- to give it a salt form of NaCl as a product. We cooled the solution in an ice bath for 15 minutes. By reduced pressure filtration using a Hirsch funnel, we collected the solid precipitate that formed in the basic solution. We washed the precipitate with 2 1 milliliter portions of distilled water. We then air dried the washed microcrystals by spreading them on a filter paper. Before the experiment, we weighed the filter paper and calculated the weight to be 0.975 grams. After the isolation took place, we weighed the filter paper with the substance and calculated it to be 0.976 grams. This means that the weight of the ethyl-4-aminobenzoate was 0.025 grams, and we originally started with 50 milligrams. Due to the spilling of our aqueous solution in the original solution, we lost about half of our substance, giving us a 50% recovery. We found the melting point of the ethyl-4-aminobenzoate to be 89 degrees, and literature value is 88 to 92 degrees Celsius, which matches with our value. Additionally, you can look at the IR graph of ethyl-4-aminobenzoate. It shows that there's stretching at about 1600 to 1700 of COO to O bond, and around 3300 to 3500, there's stretching at N to H bond. Both of these characteristics correlate to the formation of ethyl-4-aminobenzoate, which shows that our IR graph correlates with the ethyl-4-aminobenzoate, and we did the lab successfully.
In order to separate the acidic component, or the benzoic acid, from the solution, we first need to add 2 milliliters of 3 molar NaOH to the ether solution. Then, if necessary, we add an additional 1 to 2 milliliters of ether so the volume of the organic layer is at least equal to that of the aqueous phase. Similar to the separation of the basic component, we carry out extraction as before, by allowing the layers to separate and then transferring the bottom aqueous basic layer to a labeled 10 milliliter Erlenmeyer flask. We repeat the routine and again remove the aqueous layer and transfer it to the same Erlenmeyer flask. We then stopper this flask containing the extracted aqueous basic phase. Then, in order to isolate the benzoic acid from the solution, we first add 6 molar HCl dropwise to the aqueous alkaline solution that was separated and set aside earlier, until the solution becomes distinctly acidic according to the litmus paper. We create an acidic solution in order to precipitate out the benzoic acid so that we can then filter it through filter paper. We then cooled the flask in an ice bath for about 10 minutes. After that, we added a small amount of the saturated aqueous solution to the sodium chloride to help promote further precipitation of benzoic acid. We did this because only a small amount of precipitate was obtained on acidification. By using filtration under reduced pressure using a Hirsch funnel, we were able to collect the precipitate of benzoic acid. We rinsed the precipitated acid on a filter paper with 2 1 milliliter portions of distilled cold water to ensure we collected all of the precipitate of benzoic acid. We then dried solid product using one of the techniques used earlier for ethyl-4-aminobenzoate. The weight of the dry benzoic acid was 0.04 grams, and the calculated percent recovery was 80%. We may not have had 100% recovery because we may not have gotten all the precipitate out of the flask when filtering it. The melting point of benzoic acid was 121.5, and our IR spectroscopy showed that the product we isolated was benzoic acid. We know this because at around 3000 there is OH stretching, CH stretching at around 2500, and COO stretching at around 1600, which all support the formation of benzoic acid. In order to separate the neutral component 9-fluorine, we first washed the remaining ether solution contained in a centrifuge tube with 1 milliliter portions of water. Beautiful! We then separated the lower aqueous layer in each sequence. In order to separate the neutral component 9-fluoronon from the solution, we added about 300 milligrams of anhydrous granular sodium sulfate to the wet ether. We then capped the tube and set it aside while working up the alkaline extraction solution. In order to isolate 9-fluoronon, we used a syringe to transfer dried ether solution collected earlier into a tared 10 milliliter Erlenmeyer flask. We then rinsed the drying agent with additional 1 milliliters of ether and combined the ether wash with anhydrous organic phase. In the hood, we concentrated the ether solution by placing the sample under a steady stream of oxygen. The weight of 9-fluoronon after we isolated the solvent was 43 milligrams, and our percent recovery was 86%. We then obtained the melting point of 9-fluoronon, which was 80.1 degrees Celsius. After finding the melting point, we found the IR. It showed us that we correctly isolated 9-fluoronon because around 1600 there was Z-double-O bonding, CH stretching around 1550, and around 2950 there was a cyclohexane. 9-fluoronon is made up of 1 C-double-O and 2 cyclohexanes, supporting what we found in our IR spectroscopy.
What's up, Orgo fans and Mr. Grant? Hope you enjoyed that message. Thanks for watching.